All right, so welcome to the third day of AQIS. We're starting today. My name is Ben Brown. I'm here in Sydney, and I hope you're all sitting comfortably. I'm here to introduce Michael Newman. He's a postdoc at Google Quantum AI, and he's going to tell us about some work he did in the Duke group in his previous postdoc on fault-tolerant Bacon-Shor codes in trapped ion traps. So if you're ready, Michael. One more thing. If you put your questions in the chat or the Q&A, I'll try and keep an eye on that. And if it's an urgent one for a clarification, then I can interrupt Michael in his talk. But I'll probably, if it's not an urgent one, I'll leave all the questions to the end. All right. So if you're ready, Michael, please go ahead.
Perfect. Can you see my slides? I'm going to assume that's a yes. So yeah, first, okay, good. And can you see me as well?
Yes.
Yep.
Okay, perfect. Welcome to my living room. Weird times. So first, I'd like to thank the organizers for inviting me to come speak. Like Ben said, my name's Mike. I'm currently at Google as a visiting researcher, but prior I was at Duke as a postdoc in the lab of Ken Brown. And today I'm going to be talking about a quantum error correction experiment that we did in collaboration with Maryland. Sorry. And before I get started, I just want to thank all of my wonderful collaborators, in particular Laird, who was the graduate student lead on the project, Marco, Crystal, Drew, Dawe, Deborah Priya, who are all in the lab of Chris Monroe, who has now moved to Duke. And also Dripto and Muyan, who are graduate students in Ken's lab, Muyan's now at IBM, and of course, Ken himself. Okay, so welcome to the Sea of Fault Tolerance. We are aboard the SY quantum computer, and we are beset on all sides by all different types of errors. Coherent errors, crosstalk, depolarization. Some errors are not as damaging, like energy relaxation in microwave frequency ions. If you're familiar with left shark, that's left shark. But there are some problems below the surface that we need to be concerned about, like leakage and cosmic rays and other types of errors that are more damaging than the ones that I mentioned previously. And if we think about this sea, getting below into the sea is sort of like seeing beneficial error correction. And at the bottom of the sea, we have kind of the buried treasure, what we want, the fault-tolerant quantum computing at scale. So we can do things like Shor's algorithm, which we read about in Nielsen and Chuang, and we eventually want to see done. And all the while, we're keeping our eyes out for hidden dragons, really serious errors that could prevent, some particular architecture from scaling up. And we don't think there are any dragons at the bottom of the ocean, but the only way to find out is to dive in, do experiments, and see what we see. So the way I want to do this, present this talk is essentially in two parts. And the first part is going to be the experiment. And I want you to think of the experiment as kind of a marker on this road to fault tolerance. If we take a state-of-the-art ion trap system right now, and we run an error correction experiment, first of all, can we even run one? And if we can, what do we see? And then in the second part of the talk towards the end, I just want to speak a little bit about, perspectives looking forward. How can we project how difficult it's going to be to scale error correction in a device, given the component error rates that we see? And given a fault-tolerant quantum computer, what is the cost of running that computer? And how should we think about designing algorithms that will give an advantage? So in particular, I'll begin with an introduction to fault tolerance and some previous work on error correction that appears in the literature. I'll talk about the Bacon-Shor Code, which is the code we use in our experiment, why we didn't choose something a little bit more popular like the surface code. I'll tell you about the ion trap and the experiment, so you get an idea of the physical fidelities that we see and the encoded fidelities that we see. So you have an idea of how they compare to one another. And finally, I'll have this forward perspective on projecting error correction and the cost of fault tolerance. Okay, so to begin, when we think about large systems today, typically we think of 10 to 50 to 60 qubits, although that number is going up all the time. And we have these really nice experiments like the Beyond Classical experiment at Google, where essentially they were looking at a 53 qubit device and very high fidelity components. I think the noisiest thing they had was their measurement error rate, which was roughly 97%. And on the flip side of the coin, we have extremely accurate small systems. Systems that demonstrate proof of principle components like 3/9 fidelity in a 2-qubit ion chain or something like that. And we're hopeful that as we scale the qubit numbers up and we scale the operational error rates down, that we can find some pre-fault tolerant applications that are commercially viable for quantum computing. But looking long term, these really kind of holy grail algorithms like Shor and molecular simulation, we know that they take thousands of qubits, not so bad, but we know that they're extremely deep circuits. So they need operational error rates that look like one failure in a billion, one failure in a trillion. So that's unphysically accurate. So we need a way of harnessing quantum mechanics to be able to reach those circuit depths with noisy circuits. And quantum error correction is basically a solution to this problem. It's a way of trading quality for quantity. So you saw a little bit about error correction in the talk yesterday from Alex, for those of you who tuned in. And I'm just going to give you a very brief and high-level overview. So quantum error correction is essentially what you do is you encode your information into a subspace of a larger Hilbert space. This subspace is called a quantum error correcting code, and it typically has three parameters, n, k, and d. So you encode k qubits into n so that any error on at most d-1/2 of those qubits can be corrected. Typically, when we talk about quantum error correction, what you see most of the time is stabilizer codes. So a stabilizer code is just a special subfamily of these subspaces that can be expressed as the mutual +1 eigenspace of a set of n-k independent Pauli operators, right? So n degrees of freedom, k encoded degrees of freedom, n-k constraints. And error correction, in principle works pretty simply in this framework. Essentially, Pauli errors will map your original code space to a set of orthogonal code spaces indexed by these syndromes, which you can measure. And once you see some syndrome, you can apply some recovery operator to bring yourself back to the original protected code space, hopefully without modifying your encoded information. So a quick example is Steen's code. This is a very famous, the smallest example is something called the CSS code. It encodes 1 qubit into 7 to distance 3. So it's expressed as the +1 eigenspace of a set of 4-body X and Z type operators that are applied to these trapezoids that you see in this triangle on the right. And it has encoded X and Z type operators that are each 3-body operators acting on, for example, the side of this triangle. And the fact that the code has distance 3 is exactly reflected in the weight of these operators being 3. So you need to act on 3 physical qubits to modify the underlying encoded information. So if error correction is the framework that allows us to protect information, then fault tolerance is the operational language that allows us to protect it in practice, right? Because in order to correct errors, we need to find out information about our system in the form of these syndromes that I mentioned. And now these syndromes, you can't measure directly. Typically, in order to measure them, you need to couple your information to an Ancilla qubit, where you kick the errors from your data to that Ancilla, and then you measure those Ancilla qubits to look for these errors. Now, the problem is that when you apply circuits, sometimes errors propagate in ways that you don't expect or can hurt or damage your code. So for example, if we were trying to extract the syndrome from the Z-type stabilizer on the left, this red stabilizer, if we had an error that occurred during this syndrome extraction on the Ancilla, it can propagate to a damaging error on the data. And it turns out that if this configuration, if you saw the stabilizer configuration, or rather the syndrome configuration corresponding to this error, probably what you'll choose to do is actually apply, when you're doing error correction, this Z-type operator to the 3rd qubit. Now, why is this bad? Well, this is now an encoded Z-type operator that we didn't want to apply. So we've essentially dephased our encoded information, and what has caused us to dephase it is this single circuit fault, this single error. So if a single error can corrupt our encoded information, we shouldn't encode it at all. And so informally, fault tolerance is a design principle that guarantees that whatever protection you're trying to get from your quantum error correction code, you preserve it when you apply the circuits that you need in order to utilize the code. Or more formally, it's a principle that guarantees that any d-1/2 circuit faults cannot corrupt the encoded information. Okay, so now that we've had kind of a whirlwind tour of fault tolerance, let me tell you about some demonstrations of quantum error correction that have appeared in the literature. So the first thing that I would be remiss not to mention, because this is an experimental error correction talk, are bosonic codes. So bosonic codes fit a slightly different paradigm than the one I've described. Instead of encoding a qubit into many qubits, you encode a qubit into an oscillator. And for that reason, they're hardware efficient codes. And so there's been a ton of really, really great work coming out of Yale and AWS and Delft and others, looking at these types of codes as experiments that we can run today. And so, I won't be talking about these codes, but I just want to mention that there have been a ton of demonstrations where you see the memory lifetime, not a ton, but there have been demonstrations where you see the memory lifetime of the encoded qubit outlasting the memory lifetime of other components that form the oscillator. So in terms of qubit codes, which is what we'll be focusing on, there was a really nice paper that I want to point out by Innsbruck about 5 years ago. And what they did is they also encoded a qubit into a 7-ion chain in the form of exactly the steam code that I had mentioned. And this was kind of a demonstration of error correction. What they were doing is they were injecting errors onto data qubits, so applying errors themselves, measuring the data qubits, and then checking to see that the syndrome outcomes that they saw were consistent with the errors that they had injected. However, I want to point out that this, again, was not fault tolerant. The encoding circuit that they were using would not could propagate errors in a way that would immediately damage the encoded information. So in particular, in principle, they couldn't hope to have encoded error rates that were lower than the certain critical component error rates. And this was kind of reflected in the fidelities that they saw when they were preparing their states. They had fidelities on the order of 25% roughly. There's also been a lot of nice error detection work. So this is in the situation where you post-select on there being no evidence of any errors occurring in your system. And this benefits from the fact that you need fewer qubits to do error detection. So you can get away with smaller systems when you want to demonstrate this. Okay, so finally, I want to mention an experiment that I personally really like, which was by Julian Kelly and others at, I think they were at UCSB at the time, although they might have been at Google, I'm not sure, where they looked at running error correction, but on a classical code. So in particular, they ran this error correction protocol on something called the repetition code, which just protects against one type of error, let's say a bit flip error, instead of both types of errors, bit and phase flip errors. And this basically buys you three things. First of all, the code is one-dimensional, so it's easy to lay out. Second, because the code is only protecting against one type of error, the amount of the amount of noise that you can tolerate from your components is much higher. The code is just intrinsically more resilient than any other quantum code. And the third property is simply that you require fewer qubits. So again, because you're protecting against one type of error, in order to do fault-tolerant syndrome extraction or a fault-tolerant memory experiment, you only need 5 qubits to distance 3. That means correcting one fault, and 9 qubits to distance 5. That's correcting any 2 faults. That compares to the surface code where you would need 17 qubits and 49 qubits. So it's a significant overhead. Now, with all that said, they saw exactly what you would want from a memory experiment. They did many rounds of error correction, and they saw that as they increased the distance of the code, they significantly increased the error suppression that they were seeing from in their experiment. The one thing that they mentioned that they're kind of missing, and this is something that hopefully future experiments will work on, is that this error suppression factor lambda, which we will talk about later on the bottom right, they saw that as they applied more and more rounds of error correction, this error suppression factor went down and down. And this isn't what you want from an error corrected system, right? You want the error correction, the protection that you get to remain stable and not deplete over time. Because certainly the whole point of error correction is to run long circuits, and so you want your circuits to remain stable at long time scales. Okay, so that was a lot about fault tolerance in some of the previous work. So now let me tell you a little bit about the Bacon-Shor Code. So the Bacon-Shor Code was first invented in this paper by Dave Bacon in 2006, where he was looking for self-correcting quantum memories. And it's typically defined on an L by L lattice of qubits. But in this case, we're only interested in the smallest example, distance 3. So on distance 3, it's defined on a 3 by 3 lattice of qubits. Now it's a stabilizer code, and it has 4 stabilizers, 2 6-body Z-type stabilizers that act on pairs of columns, and 2 6-body X-type stabilizers that act on pairs of rows. Now, that's 9 physical qubits and 4 constraints, which means there's 5 degrees of freedom left over. And one of these degrees of freedom is special. It sits apart from the other 4. And this is the degree of freedom in which we are going to encode our logical information. We're going to have our protected qubit. And it's special because the encoded operators on this qubit are all weight 3, which means we can do error correction on this qubit. The other 4 qubits are typically called gauge qubits, and collectively they form what's called the gauge subsystem, and we're going to allow these to vary freely. And so in particular, this is something called the subsystem code, because you're encoding the information into a subsystem of the code space, where the code space here is, 2 to the 5 dimensional, 32 dimensional. Okay, so the question that I get most often about this work is, why did you choose to use the Bacon-Shor code instead of something more popular like the surface code? And the answer is really for 2 reasons. The first reason is that you require fewer qubits. So it turns out that when you run error correction on the surface code, you have 9 physical qubits and 8 ancilla qubits, 1 for each stabilizer generator. On the Bacon-Shor code, you can actually get away with the same trade-off. You have 9 physical qubits and you have 1 ancilla qubit per stabilizer generator, but now there are only 4 of them. Now it seems like a small savings, 4 qubits, but when you have a 15-ion device, it's very helpful because we want to run the smallest experiment that we possibly can to see the highest fidelities that we can for now. And now you might be a little bit surprised that syndrome extraction here is fault tolerant. And the reason you might be surprised is the stabilizers are kind of big. So you could think that errors on the ancilla qubits could propagate to high weight correlated errors on the data qubits. And this can happen if you don't do things in a clever or in the correct manner. So if you look in this second square from the left, if you measure in this order, 1, 2, 3 going up and 4, 5, 6 going down, and this red's a controlled NOT gate fails, let's say you have a Z error on your ancilla qubit, then this is going to propagate to qubits 4, 5, and 6. And if you look down here, this is exactly the encoded phase flip operator for the logical qubit we're trying to protect. So this is a catastrophic failure of error correction. A single circuit fault has unwantedly applied a phase flip operator to the protected information. So that's not good, but it turns out that if you instead measure in a different order, in a very particular order, 1, 2, 3, 4, and 5, 6, again, you have the same phase flip operator. It will propagate to these pairs of rows of qubits. Now it's an even higher weight operator, but it turns out that if you play with the stabilizer group for just a little bit, this is actually just applying a phase flip operator to one of these gauge degrees of freedom whose state we allow to vary freely. And so if you play with this a little bit, you'll pretty quickly convince yourself that this syndrome extraction is in fact fault tolerant. So what's kind of going on here is these passive degrees of freedom, by allowing them to vary, they're protecting us against these, a priori high weight errors that can occur during syndrome extraction. Now, the second property about the Bacon-Shor code that is really fantastic is that you can prepare it unitarily and fault tolerantly. So if you wanted to fault tolerantly prepare the surface code, the way that it's typically done is you initialize all of your qubits in the 0 state, for example, if you're preparing 0, and you turn on your stabilizers. And when you turn on your X-type stabilizers in particular, you're going to project onto a random syndrome version of your code space. And repeating this, this syndrome extraction for a few times, you effectively have prepared your surface code fault tolerantly. Now for the Bacon-Shor code, it turns out that if you carefully choose which gauge state you prepare into, the state will decouple into a product of 3 independent cat states. So for those of you who are familiar with Shor's code, this is where the Shor in Bacon-Shor comes from. And so because those cat states are decoupled, they can be prepared independently. Now the encoded information is stored in the relative phase of these 3 cat states redundantly. So if a single circuit element fails, perhaps one cat state will fail altogether, but the 2 other cat states, having redundantly encoded that information, you can extract it from that redundant encoding. And you can do this for both 0 and plus. It just changes the basis of the cat state and the orientation of the cat state. So, why does this matter? Why is being able to prepare things unitarily give us anything? And it's for 2 reasons. First of all, if your device cannot perform intermediate measurements, as our device cannot yet do, and I'll explain what kind of effects that has on error correction later, well, then you're stuck using something that can be that must be prepared unitarily, because you just don't have the option of projectively preparing some state. The second thing is that this is actually a much shorter circuit, right? It requires much less work to prepare 3 cat states than to measure the stabilizers of the Bacon-Shor code. It would require 24 entangling gates to measure stabilizers compared to 6 entangling gates to prepare these 3 independent cat states. And we're going to see that that's a significant benefit when you're running a small memory experiment. Okay, so the last thing that I want to mention is fault-tolerant measurement. So fault-tolerant measurement works pretty much the same as in any CSS code, but I just want to illustrate how how error correction is being done. So what you do when you fault-tolerantly want to find out the encoded observable information from your error correcting code is you individually measure each physical data qubit, and you see what outcomes that you get. So let's say we're measuring the encoded Z observable. And then what you do is you look at the relative parity of, in the support of a stabilizer. So you look at the correlation the stabilizer should obey, and you see if it's violated. So for example, we know that the sum of these outcomes should be even, but they're odd, which indicates that some error has occurred in our system. Now, given that information, together with any other syndrome information that you've previously extracted, you'll perform error correction using some decoding method. So in this particular case, it turns out that a reasonable choice of correction would be to flip this bit. And then finally, having corrected the information, you choose some representative of your logical observable, for example, this far left column, and you declare whatever the parity of that observable is to be the encoded observable's outcome. So in this case, it will be even. And I just want to point out that there's nothing strange about doing things this way. Even if you were running a long-term memory experiment, this is the final step that you would have to run in order to extract the logical observable information. So if we were running many rounds of error correction, which unfortunately we cannot yet do, this would still be the final step. This post-processing is a necessary step. Okay, so I mentioned that the Bacon-Shor code is particularly good for small-scale experiments, and this was quantified in a nice paper by Muyan Lee, Daniel Miller, and Ken back in 2018. And so what they looked at was, if we wanted to run a small experiment in an ion trap motivated error model, what code should we choose? And what they saw is that because of this simple preparation circuit, if the memory experiment is low depth, so let's say 1 cycle, then the error that you could tolerate to realize some break-even point, and now break-even is a kind of a hard concept to, it's kind of a tricky thing to define, but in this case, they have a single parameter noise model, so it's not as hard. But if you wanted to reach this break-even point, you could tolerate noise that was 5 times, components that were 5 times noisier when you use the Bacon-Shor code instead of the surface code. And it's really mostly just coming from this preparation step that's just much simpler. Now, of course, asymptotically, the surface code is significantly more robust than the Bacon-Shor code. For those of you who know a little bit about error correction, very famously, the surface code has a threshold and one of the highest thresholds, whereas the Bacon-Shor code doesn't have any threshold at all, which sort of means that in the asymptotic limit at any fixed error rate, as you scale up, the Bacon-Shor code cannot realize an arbitrary error suppression. Now, the way that this manifests when you're doing many rounds of error correction is that you get this initial boost on the right here from using the Bacon-Shor code, but as you run a longer experiment, the surface code and its robustness wins out. So you lose this initial gain from this simplified preparation circuit. Now, with that said, if you're only running 0 or 1 rounds, which is what I'm going to be describing a bit later, then the Bacon-Shor code is a pretty good choice. Okay. So I've told you about fault tolerance. I've told you about previous demonstrations. I've told you about the Bacon-Shor code. Now let me tell you about the ion trap in which we're going to perform this experiment. So this ion trap is 15 ions long, although the 2 ions at the endpoints are spacer ions just to keep the spacing between the computational ions even. And the qubits themselves are ytterbium-171 ions, where the qubit states are encoded into the hyperfine ground states of these ions. Right, so this is a microwave frequency transition, and the T1s are extremely long. So it's essentially not an error at all. If you remember that picture of the sea of fault tolerance, that was the left shark, again, if you're familiar with the meme, version of our error. Now these are clock states, which means they're first order insensitive to the magnetic field. And so we still get very long or pretty long T2 times. So the T2 time of this ion that we measure in the 15 ion chain is about 2.5 seconds. and we get a T2 star of about 600 milliseconds. So the qubits themselves are relatively pristine. We have, fairly accurate qubits. The preparation and measurement is also fairly good. So we prepare our states via optical pumping, where we basically drive some transition from the 1 and these Zeeman split states until we recover the 0 state. And we perform measurements by driving this transition from this 1 state up to from the S manifold up to the P manifold, and we collect any photons that are scattered in this process. So if an ion fluoresces when we drive this transition, we know that it's in the 1 state, and if it doesn't, we know that it's in the 0 state. Now, the problem with doing that is, well, as you're scattering these photons, it turns out that you could have to measure the entire chain all at once. So we do not currently have the ability of running intermediate measurements on this device. In particular, when you measure the chain, you have to measure the chain all at once. Now, the state preparation and measurement errors that we see are about 0.5% on average, 0.22% for the 0 or the dark state, and 0.71% for the bright state, where the asymmetry is coming from accidentally pumping the 1 state to the 0 state before any photons have been collected. The single qubit gates that we run are probably the most accurate component in the device. When we did randomized benchmarking on the 15 ion chain, we saw a 1 qubit gate fidelity of roughly 99 about 4 nines fidelity. So this is the most accurate. This is the most accurate component, which brings us to the least accurate component, which is the 2 qubit gate. So in ions, the way you entangle a pair of ions is by using the shared motional modes. And we use something called the Molmar-Sorensen gate, which is basically just a resilient 2 qubit gate. And the native ion trap operation is basically applying some Ising Hamiltonian. So you have this XX interaction where it takes about a little bit north of 200 microseconds to entangle 2 qubits in the chain. So this is, this is far and away the slowest operation in our device. But I should say that we can address any pair of ions, right? You've probably heard about this all-to-all connectivity in ion traps, particularly in a small chain like this. We can entangle any 2 ions that we want. And this is going to be important because in the Bacon-Shor code, we have to measure 6 body stabilizers, which will require a lot of different connections. Now, not every pair of these connections is made equal. Some couple more strongly than others. And we use a cost function, which is basically the laser power that was required to do some particular coupling. And we want to minimize that power because it causes stray interactions like crosstalk that can cause errors in our device. And so for a typical 2 qubit gate that we're using in our experiment, right, we're not using every pair, but for a typical pair, we see a fidelity of about just south of 2 nines, so about 98.9%. So again, it's fairly accurate, although it's not as accurate as the components that I've described previously. So just to summarize, I just want to compare some of the things that we see in our chain versus the state of the art. And again, the chain doesn't realize, it doesn't quite get to the state of the art in any single component. This isn't particularly surprising because often the state of the art is shown in small ion chains, whereas on the right-hand side, we're operating with a system that's large enough to run error correction. I think these fidelities are pretty impressive. And I'm not bragging because I had nothing to do with it. This is just the folks at Maryland doing a wonderful job tuning up their device. Okay, so that gives you an idea of the platform that we're working with. Now let me tell you about what experiments we ran. And we essentially ran 3 experiments. We did fault-tolerant preparation and measurement, fault-tolerant logical gates, and fault-tolerant syndrome extraction. So to begin with, I've already described how you can prepare these 3 cat states independently, and then we can measure them. So it turns out the Bacon-Shor code has a fault-tolerant encoded Y rotation on the encoded block sphere. It's a transversal gate for Bacon-Shor up to permutations. You learned about transversal gates from Alex yesterday, hopefully. And what we see is exactly what we would hope to see. So you want to focus on these blue bars here. So this is just reading out the encoded observable before doing any error correction. And you can see that we see errors that look roughly like 5%, and over for plus and minus more like 10%. After we do error correction, so using the stabilizer information correlations to fix the state, these numbers get reduced by about an order of magnitude. So this gets down to about 0.2% and 0.4%. And if you'll recall, the physical spam in our system was 0.22% for the dark state, so about the same as this, and 0.72% for the bright state, so even higher than this. So here's an example where you see that the encoded qubit is actually outperforming the physical qubit, which is, I think is very exciting. Now, the other experiment that we did was we also tried to prepare these states non-fault tolerantly. And what we did is we basically took the information encoded into the first ion and then entangled all 9 qubits by applying these initial 2 control NOT gates. Now, clearly this is not fault tolerant. And one way of seeing that is that at some point the information is encoded in this first wire. So it's corrupted there, it's corrupted, the whole way through. And what we saw is what we would expect, which is that, fault tolerance is better than non-fault tolerance. We saw that the fidelities, even when you're doing corrections, stayed significantly above the fidelities when you're doing things fault tolerantly. Now, I just want to pause and kind of play devil's advocate for a second. You could make fairly, I would say, the argument that the reason that these fidelities are lower, maybe it's not fault tolerance, maybe it's just that the circuit is longer. You have to apply more gates, and so there's more opportunities for things to go wrong. But I actually think the detection experiment is probably the best signature of fault tolerance taking place. So in this detection experiment, we just post-select on any, we post-select away any runs where there's some stabilizer violation, where we've detected some error. And when you do this fault tolerantly, you see that, I think this is over 60,000 shots, we saw maybe 1 failure in this entire experiment. And it's not hard to see why. If you're doing things fault tolerantly, 3 independent components from this circuit have to fail in order to fool this experiment, because you have to, essentially in a single shot, have accidentally implied an encoded operator. But when you look at the detection error rates, particularly for plus and minus, but also for 0 and 1, you're still seeing error rates that are like 1.5% roughly, right? It's half this number because we're recording the plus minus 1 observable. And it's not hard to see how this error can come about, because when you're doing things non-fault tolerantly, any error on this wire initially or a correlated error on this 2-qubit gate can immediately propagate to an unwanted encoded operation. And I think the extreme contrast between these 2 sets of data is an excellent signature for fault tolerance, really doing what we would hope it would do and what we thought it would do, which is make the fidelities much better. Okay, so we also did an idling experiment. So this is just essentially a Ramsey experiment where we prepared a plus state, allowed it to decay for some amount of time, and then saw how well we could recover the state. And I want to say that this isn't exactly the experiment that you would want to run on a logical qubit, right? Because in practice, what you would want to do is you would want to stabilize this qubit in real time by doing syndrome extraction repeatedly. Now, as I've mentioned, we don't have the capacity of doing that yet. So rather unsurprisingly, this is going to be much worse than the physical T2 star, because, well, you're preparing a giant, entangled state, and you're allowing it to decohere without really stabilizing it until the very last step. But nonetheless, we saw a significant benefit from running error correction, right? About a 3 times benefit. And also, as we did all these experiments, we were testing these against the error models that we thought described what was going on in our device. And we saw that this was, this dephasing, this encoded dephasing, was extremely well explained by just the physical dephasing. So there weren't any hidden, dephasing errors that we really weren't accounting for at a larger scale, which is comforting. We also applied fault-tolerant logical gates. So like I mentioned, the Bacon-Shor code has certain transversal gates. And we compared these also to certain non-fault tolerant gates. Again, this direct preparation circuit that I mentioned before, but also this continuous rotation. If you'll remember from Alex's talk, this is necessarily non-fault tolerant because it's a continuous rotation, or at least it's not transversal. And we saw what you would hope to see, which is that the fault-tolerant gate outperformed, its non-fault tolerant counterparts, and the fidelity increased as we applied correction and then detection. Right, detection is always going to be the best possible fix for the state. Now, we tried to compute a 1-qubit error rate, and we saw something on the order of 99.7%. So this is pretty good. If you'll recall from the 1-qubit physical error rate, we saw 4 nines there, where this is closer to 3 nines. So you might say, well, it looks like this is just much worse. And to that, I would say that this is a little bit of an apples to oranges comparison for 2 reasons. One, when we were trying to assess the fidelity of the physical gates, we were running randomized benchmarking. Here, the way that we did it is we fit a decaying exponential to this curve of states, and we saw whatever that decay parameter was, we declared as the fidelity. So it's a little bit of an apples to oranges comparison. And again, any experiment involving the encoded information, in order to run it, we had to run these 2-qubit gates that were the most faulty part of the experiment. And these 2-qubit gate fidelities were much lower. It is not as good as the 1-qubit gate fidelity for the individual physical qubits, but I'm still, I think that it's pretty promising that it's still a very reasonable fidelity. And I just want to mention that because we're non-fault tolerantly preparing states in the XY plane, one thing that we did was we also prepared the H-magic state, which is a resource for universal fault-tolerant quantum computing. And we estimated a fidelity of roughly 98%. So we could prepare these magic states with reasonably high fidelity, which was nice. The last thing I want to mention is fault-tolerant syndrome extraction. So the experiment that we did here was we encoded the 0 state fault-tolerantly. We manually introduced an error. So this is much like the Innsbruck experiment. But then what we did is we demonstrated mapping all of that information, that error that we injected, onto the stabilizers themselves, so onto the syndrome qubits. And then we measured the state globally. And what we saw is what we would hope to see, which is that if, for example, you applied a Z operator to the 9th qubit, the syndrome that you saw, the ancilla populations, exactly reflected whether the corresponding stabilizer, which anti-commuted with that error, in this case, this dark blue, right, this dark blue stabilizer here, fit the correct, it was correctly flipped. And then when the stabilizers commuted with whatever error we injected, it was correctly, not flipped. Now, unfortunately, if you look at this identity injection right here, you'll see that there's roughly a 20% and probably closer to 25% kind of false positive rate. And so these are errors that we didn't inject, but just during the course of running syndrome extraction, we likely, unwantedly injected into the system because our components are noisy. And if you're kind of familiar with detection fractions, this is just too much noise to handle for us to really expect to get better results by doing syndrome extraction. And it's not really hard to see why. If you compare the encoding circuit to the syndrome extraction circuit, the encoding circuit is just much smaller. Whereas the syndrome extraction circuit, it's quite a deep circuit, especially for an ion trap. And so what this syndrome extraction circuit is doing is it's giving you 4 extra bits of information about the errors occurring in your system. But the amount of entropy that it's injecting into your system just by running it, it's not worth those 4 extra bits of information yet. And so what we need to do is we really need to make our components more accurate, particularly the 2-qubit gate, if we want to be able to stabilize a qubit over many rounds of syndrome extraction, even assuming that we had intermediate measurements in the system now. Okay, so to summarize, here's kind of a comparison of the physical fidelities in our device and the single shot encoded fidelities that we saw. Again, the T2 star is quite low because we can't stabilize the state over many rounds of syndrome extraction. The spam is quite nice, so we actually see an example of the encoded fidelities performing better than the physical fidelities. So that, I think that's really exciting. The 1-qubit gate error, again, it was quite high, not necessarily as high as the physical fidelity. But again, just to reinforce the point, all of these numbers on the right were in experiments involving this really noisy component, this 2-qubit gate, which is only accurate to just under 2 nines. And so something that I really am excited about that the Maryland team I think is working on is trying to demonstrate a 2-qubit gate. So a 2-qubit encoded gate rather. So between 2 Bacon-Shor encoded qubits and seeing what the gain is, because that would really be an apples to apples comparison of the noisiest component in the system. And I just want to mention that if you're going to do error correction for an ion trap, the limiting factor is really the 2-qubit gate. So you really want to be, if you want to run a longer circuit in an ion trap, the 2-qubit gate is going to be what's preventing you from doing so. And so we really hope that this 2-qubit gate fidelity, just for this toy experiment, shows an improvement when you encode the information. Okay, so I'm running a little bit behind, so I won't say too much about this, but what are some next steps that we can run? So the first thing is that, as we saw from syndrome extraction, the 2-qubit gates just need to get better if we want to run many rounds of syndrome extraction and expect to see an improvement. And the second thing is that, of course, we need to, in order to run many rounds, do intermediate measurements. Now, one way of doing that, which is a fairly popular proposal, is to split the chain up into pieces. measure individual parts of the chain, so one of these individual pieces, and then merge the chain back together. Now, it turns out that when you do this, the chain heats up in this longitudinal motional mode. And this can be pretty problematic. It'll kind of decrease the fidelity of your 2-qubit gates. So you need something called, you'll need something called sympathetic cooling to make the device stable over many of these merges and splits. And so this is something that, a lot of groups are working on, hopefully we'll get running so that we can run these many rounds of syndrome extraction that we want to do ultimately. Okay, so that was the part about the experiment. So, we've gone through, you've seen what fault tolerance is, you've seen previous demonstrations. Now you have an idea of what the encoded error rates would look like in an ion trap device of today. So let's talk a little bit about, how you can project what sort of error rates you're going to need moving forward to scale your device up. So the first thing that I want to mention is this, a figure of merit that I think is a really good one, which is this error suppression metric lambda. And it appeared in this. It's appeared many times. One example is in this paper by Julian and others. And what lambda is, it basically tells you at the physical error rate of your device right now, if you increase the size of your code, how much are you reducing the encoded error rate by? Now, this is closely related to the threshold that I had mentioned before, but it's not exactly the same. So, for example, there are decoding schemes which don't change the threshold at all, but can almost double lambda when you're well below threshold. And this is the regime that we want to be in. We don't want to be near the threshold if we want to scale up error correction. We want to be well below it. And so if you had invented such a scheme and you said, oh, the threshold is the same, I don't want to do this. But it turns out that you can significantly reduce the overhead of your device by running this other scheme. So I think it's important to look at this lambda factor. So it's good because it predicts the resource requirements for scaling up your device. It's bad in the sense that it's hard to test, right? You need a distance 5 if you want to do the surface code, 49 qubits to run to measure this parameter. But I think it's an interesting figure of merit and one that should garner maybe more attention than it does. So one analysis that I particularly like, which is something that I have to thank Cody Jones for, this is something that he put together, is trying to describe lambda in terms of its individual component error rates that you expect to see in your device. So in this picture, essentially what's going on is that we've linearized lambda as a function of different component error rates that we expect to see in this particular case in a superconducting quantum computer. And each of these little bars corresponds to one of these error processes. So I think this one, for example, is, if I recall correctly, idling during a long measurement time. So idling on the data qubits during a long measurement time. And so what you can see is that this gives you a nice way of visualizing how much each of your component error rate is contributing to this error suppression factor, where you want to make this error suppression factor. In this case, it's plotting an inverse lambda, so very low. And so if we take roughly components that we see today, you might expect an error suppression factor of about between 3 and 4 in the bit flip code, and less than 1 in the surface code. And this is saying that if we built a surface code of distance 3 and distance 5, and our error rates stayed exactly as they were today, we would not see an improvement. In the bit flip code, you would see an improvement because, again, that code is just intrinsically more resilient than the surface code. It can tolerate more errors. So one thing that I think is really an exciting prospect and a nice demonstration of error correction would be to demonstrate a lambda greater than 1 in the surface code. And this is something that I think a lot of teams would be interested in doing. In particular, you can look at each of these individual component error rates, which I unfortunately haven't labeled, sorry about that, but you can just imagine each of these individual component error rates, and you want to get them down to, or you want to predict what they have to be in order to hit this, for example, proof of principle experiment. Now, even if you get lambda greater than 1, so even if you get below this threshold value, you really need to get lambda quite low to realize error correction in a manner that isn't exorbitantly expensive. So for example, if you look here at this lambda equals 1.4, if you try and project on the back of an envelope what the qubit overhead will be for running such a code, it's about 32,000 qubits per logical qubit. So it's really expensive. And so one thing that we're kind of aiming for at Google is ultimately getting down to a lambda of 10. We think we can get the component error rates down to these very, very small slices that you see here. And if you get your error suppression factor all the way down to a lambda of 10, then it's still expensive, but you only require 800 qubits per encoded qubit, which is a lot less than 32,000. Now, of course, if you look at a simple error model like this, it misses a lot of very, very damaging noise sources, like leakage, where your information leaves your computational subspace. For ions, ion chain heating, where your gates sort of under-rotate over time due to this longitudinal motion that I mentioned. Or cosmic rays, every few seconds, you have this, something imparts a huge amount of energy to your system and it causes a massive correlated error. And each of these error sources don't really play well with error correction. But the only way to find out exactly, how the device is behaving with each of these is to just run it and see how it does. And so, I think that we're in a pretty exciting time where we can run error correction experiments, see what happens, and then, start iterating on our plan is for scaling up by looking again at these component type error rates. Okay, so final thing that I wanted to talk about is the cost of running a surface code quantum computer. So we've discussed what encoded qubit might look like today, or what it does look like today. We've chatted a bit about how you can predict the scaling requirements for an error-corrected quantum computer. Now, let's say that we succeeded. We built the fault-tolerant quantum computer. We have it here. What kinds of algorithms do we want to run on it? Where can we see a quantum advantage? And the reality is that running the computer is itself extremely expensive. So you don't need to know too many of the details here, but it turns out that if you want to correct at least a surface code-based quantum computer, you have to be solving this graph problem, this online graph problem. It's a three-dimensional matching problem in real time. So you've got your quantum computer running along, and you've got this classical computer, which basically is going to be co-processing all these errors and telling you where the errors are occurring and how to fix them. And this is a significant amount of classical co-processing that's required. So this is something that I've worked on, in the past, and in particular, you want this classical co-processing to be as cheap as possible. So typically, the way that this decoding is done is that it's done using this minimum weight perfect matching algorithm, which is a relatively efficient algorithm. But again, you want to make this as cheap as humanly possible so that you're not running some massive classical computation alongside your quantum computation. One thing that we've been working on, me together with Craig Gidney and Cody Jones and Michael Broughton, is looking at approximate matching decoders, which essentially recoup the performance of a standard minimum weight perfect matching decoder, which is nice, so in terms of accuracy, but also runs very efficiently. So here's a plot of like on the x-axis, you have the distance of a surface code that it's decoding, and on the y-axis, you have the number of nanoseconds per round of syndrome extraction that it takes to decode the information. And a good bet for the size of a distance code that we'll need in the future is roughly a distance of 25. And so at distance 25, this process would take about 700 nanoseconds per round of syndrome extraction, of information coming in from the device. So in particular, to decode a space-time volume of a 25 by 25 by 25 block, it takes about 17.5 microseconds. Okay, so why am I bringing this up? Well, you can do a pretty simple resource estimate of a fault-tolerant quantum gate and a classical gate. And there was this nice paper by Ryan and Jared McLean and Craig Gidney, I think Sergio and Sergio Boisio and Hartmut, where they looked at comparing the cost of running a fault-tolerant quantum analogous to the quantum NAND gate and a classical NAND gate. And how expensive are these two things relative to one another? So of course, a classical NAND gate on a modern computer that has a clock rate greater than 1 gigahertz takes less than a nanosecond. So it's extremely efficient. Now on the left-hand side, what you're seeing is, like I said, it's the analog of a NAND gate. It's really a Toffoli magic state distillation factory, for those of you who know what that is. But the important part is just the size. This is it's an enormous cost just to produce this quantum NAND operation on a surface code quantum computer. And if you think about just the amount of information you have to process in order to decode this thing on the left, just run that highly efficient decoder on this object, the amount of time that it'll take is roughly 14 CPU milliseconds. Now that might sound fast, But it's really not, right? Because it's about an order of 10 million slower than this, classical NAND operation. And so the conclusion of this paper that I mentioned is that you really have to be careful about what sort of advantages you're looking for when you design a quantum algorithm, because there's an enormous overhead just in running the fault-tolerant quantum computer if you expect your algorithm to require deep circuits. And so even if you get an advantage asymptotically, you have to worry about this overhead if you want to see an advantage in practice. And I want to mention there was another paper very similar along these lines by Earl Campbell, Ashley Montanaro, and someone else, I forget. Sorry. But so my point is just that it's really important to look at these, it's really important to look at this overhead when you're judging whether or not you can see a quantum advantage with a particular algorithm. Okay, so I just wanted to conclude with some final thoughts. First of all, I think it's a really exciting time to be in quantum error correction. We're just getting to the sizes and fidelities where we can start to run error correction experiments. If you think about the error correction experiment that we ran in this device, we basically played every trick in the book to get this to work, right? We used like the smallest code that we thought was just very resilient in a small experiment, and we were just barely eking out, in very particular cases, encoded error rates that were better than physical error rates. So it's clear that we still need much lower error rates and even additional pieces altogether, like shuttling, to build a long-lived memory experiment, which is, I would say is the, a really amazing next step that everyone would really like to get done. And as we run these experiments, we can refine our fault-tolerant procedures based on the, the errors that we're seeing. And understanding these error mechanisms will help to predict device requirements going forward. In particular, what sort of component error rates are we going to need if we're going to really get scalable error correction? And the final point that I want to make is that fault tolerance is really expensive, right? Fortunately, there are many promising ideas to make it less expensive that people have been working on. On the engineering side, making these, this big factory that you saw, this big gate much smaller, doing, different routing operations for something called lattice surgery. So there's great work by, Daniel Latinsky and Craig Gidney. There's more sort of theoretical approaches like finite rate codes, which, have been developing over many years and, could end up being, could end up having a significant savings if you can get the technology to work with it. I'll shout out to Ben, these biased error model ideas, which we could, significantly reduce lambda because you're reducing, you're only trying to correct one type of error and, realizing those physically in cat codes, that was some nice work by Yale. And so I think it's really exciting because we think we have a way forward with the surface code, for example. But we would definitely like to see some, reductions in the overhead of fault-tolerant quantum computing moving forward. And with that, I leave you once again with this sea of fault tolerance. We're kind of just getting our feet wet, and I think it's really exciting to dive right in, run experiments, and see what happens. And with that, I'd like to thank you for your attention.
All right, thank you, Michael. Yeah, give your gratitude in the chat or with the emojis or any way you can within the constraints of the medium. Yeah, no, that was, yeah, so we have 5 more minutes before the end of the hour, so we can take any questions. I don't see any just yet. So maybe I can ask a quick one.
Sure.
While we get some more. Did you, in the experiment that you did run, did you get any indication of what, did you see any dragons? Or like, did you see any dragons on the horizon?
No, I wouldn't say that we saw any dragons. I mean, what I think we did see is something we knew that was there, which is that the ion chain would heat up over time, which basically means that, you have this longitudinal mode of motion where the ions are shaking left and right. And then when they're shaking left and right, when you're shining these 2-qubit lasers on them to drive an entangling gate, they're not quite in the center of the beam. And so what ends up happening is that you under-rotate the gate, right? Because you're not really delivering all the power that you intended to deliver because the ions are moving around. So that's something that, the experiment kind of shone a light on, how much of a problem that is. And so, I think that's something that, Chris Monroe's group has worked a lot on and kind of characterizing that issue and how you can solve it. But no hidden dragons thus far.
No hidden dragons thus far. All right, any more questions? Or are we all going to go to lunch a little bit early? Just looking. No, nobody. What do I do? Do I count down? Raise the hand.
You can count down if you want.
Count down, or right? Let's see. Yeah, 3, 2, 1. Oh, I guess. Oh, there we go. No, well, that was a great talk, Mike. We can go a little bit early. Yeah, thanks everybody for coming, and yeah, thanks again. Please show your appreciation with the emojis, and yeah. So the organizers have encouraged the participants to go over to the Gather Town for some online conference interactions. Yeah, thank you very much, and I will sign off.